This call is now being recorded.
Okay, good morning. Up to now, we will complete the syllabus of finite automata, regular expressions, and conversion of FA to RE and RA to FE. And next, construction of push-down automata. Construction of push-down automata for several languages. Now, today we'll complete the topics of conversion of CFG to PDA and TDA to CFG, LBA and Turing mission. Okay. There is a procedure for conversion of CFG to PDA is if we have the production in the form of AS, S tends to AS, S tends to AS. Here the production is nothing but delta of Q comma epsilon comma here the starting symbol yes and AS Q comma AS. It is for the production S tends to AS. If the production is in the form of S tends to AS, then the push-down automata transition is delta of Q comma epsilon comma S is equal to Q comma AS. Q comma AS. In the same manner, S tends to epsilon, we need to write delta of Q comma epsilon comma S is equal to Q comma epsilon. Okay, it is the production it is the grammar for the production S tends to AS or epsilon. In the same manner, S tends to have, sorry, A tends to have 0 A1 and 0 1. So for this productions Q epsilon A, here Q epsilon A is equal to Q comma 0 A1, Q comma A1, Q comma 0 1. This is the transition function for the given production A tends to 0 A1, 1A or A1 or 0 1. And next one, in the given grammar we have 0 and 1 are the non-terminal symbols. 0 and 1 are the terminal symbols. Then we will write delta of Q comma 0 is equal to Q comma epsilon. It is the fixed production. And for 1, delta of Q comma 1 is equal to Q comma epsilon. So to convert the given CFG to PDA, we have only one transition rule. Here, for example, if the production is in the form of A tends to alpha, we will write as delta of Q comma. Here it is common. Delta of Q comma epsilon comma A is equal to. It is also common. The alpha is here only. Delta of Q comma epsilon comma A is equal to Q comma alpha. Okay. Next one. For all small a belongs to T, add the following transitions in the PDA. For example, if you have the terminal symbol in the grammar is A, then we write the production as delta of Q comma A comma A. Delta of Q comma A is equal to Q comma epsilon. If you have 1 comma 0 as the terminal symbols, then we will write delta of Q comma 1 is equal to Q comma epsilon. In the same manner, delta of Q comma 0 is equal to Q comma epsilon. The two productions are given grammar. Okay, it is the process for converting CFG to push-down automata. CFG to push-down automata. Okay, we'll see one more example here. We see one more example here of conversion of CFG to PDA. We will take one example and we will draw the answer. Okay. Okay. I will take this grammar S tends to 0 S1 or capital A. So S tends to 0 S1 or capital A, and one more production, A tends to 1A 0, A tends to 1A 0 or S or epsilon, or S or epsilon. So now we will convert the given productions to transition functions. Okay, so it is delta of q comma epsilon comma s is equal to, for this production I am writing here, delta of q comma epsilon comma s is equal to q comma 0 s1. In the same manner, it is q comma capital A. Okay, here delta of q comma, sorry, delta of q comma epsilon comma capital A is equal to q comma 1a 0, 1a 0, and one more production q comma s, and one more production q comma epsilon. These are the two main productions, and here we have a 0 and 1. The for 0 and 1 we write q comma 0 comma 0 is equal to q comma epsilon. The same manner, delta of q comma 1 is equal to q comma epsilon. This is the Pushdon automata for the given grammar. Pushdon automata for the given grammar. Okay. Pushdon automata for the given grammar, s tends to 0 s1 or a tends to 1a 0 or s or epsilon. Okay. Okay. We will take one example now to convert here. Okay, s tends to 0 bb, s tends to 0 bb, and next one b tends to 0 s, b tends to 0 s or 1 s or epsilon. So for this grammar, for this grammar, for this grammar, we'll write a delta of q comma epsilon comma capital S tends to or is equal to q comma 0 bb, and delta of q comma epsilon comma b is equal to q comma 0 1 or q comma 1s or q comma epsilon. For the terminal symbols, q comma 0 is equal to q comma epsilon, q comma 1 is equal to q comma epsilon. Okay, it is the conversion of CFG to PDE. Okay, next we will see the procedure for conversion of PDA to CFG. Okay. So here it is also one of the easiest procedure. So see here, these are the productions, or these are the transition functions. These are the productions for the transition functions. Okay. So here it is the initial production for all grammars, and for this production q naught b z naught is equal to q naught z1 z naught. Here q naught q naught, here z naught z naught, the b here, here the b, next z1 z naught, here z1 and z naught, it is the q naught here, it is the q naught here. Okay, I will write here delta of q naught comma b comma z naught is equal to q naught comma z1 comma z naught. It is written as here q naught z naught b q naught z1 z naught. Here there is only one possibility q naught q naught. Here this q naught here. Here this q naught here. Okay, in the same manner for the production 2 is also common. And here q naught z1 q naught q naught z1 q naught tends to small e. Q naught z1 q naught tends to small e. In the same manner q naught z naught q naught tends to epsilon. Q naught z naught q naught tends to epsilon. Okay, q naught z naught q naught tends to epsilon. This is the conversion of PDA to CFG. Okay. Here, we already know the deterministic finite automata. The example for deterministic finite automata is a power n, b power n, where n greater than or equal to 1. Here, coming to the previous three missions, finite automata and Poisson automata and linear bound automata, these three missions contains a number of restrictions to perform the following operations. So now we'll see about the most important topic and the very powerful machine in the theory of computer science is Turing machine. It is a powerful machine which could simulate any modern computer. So it is nothing but it can perform any operations which performed by the finite automata, Poisson automata, and linear bound automata is also okay. Next, Turing machine is a seven tuple machine. Q comma summation comma tau comma delta comma q naught comma b comma f. Okay, it is the representation of Turing machine. At the end, the blank symbols will represent the end of the given string, tape head, and finite control. Turing machine is a finite automata with an extra power, with the with the right to left and left to right movements. Okay. So L is equal to 0 power n, 1 power n. For example, if you want to construct the Turing machine, if you want to construct the Turing machine for the language L is equal to 0 power n, 1 power n, I will take a 0, 0, 0 and 1 here, 0, 0 and 1. So here the procedure is only a single point. For every 0 appeared in the input tape should match with for every 1 in the input tape itself. Then the language is said to be acceptable, otherwise it is rejectable. Okay, here for the given 0, there is a map of given one. Okay, for every 0 we need to map for 1. So here it is replaced by x and the 1 is replaced by y. The same manner second 0 and the second 1, third 0, third 1. Here it is third 1. If it goes to blank symbol, then machine is said to be accepted. Okay, in the same manner, if the grammar is 0 power n, 1 power n, 2 power n, then the input tape is 00, 11, 22, 00, 11, 22. So here first it is replaced by x, it is replaced by y, it is z, and again it comes back, it is replaced by x, it is replaced by y, and it is replaced by z. Okay, we'll see the representations here. For the language, L is equal to A power n, B power n, C power n. When n greater than or equal to 1, if I take the input tape is double A, double B, double C. Here, this language is not possible by normal push-down automata, and it is possible only by two-stack PDA. It is possible only by two-stack PDA. So, the Turing machine will solve the problem by it contains the blank symbols in the left and blank symbols in the right. The blank symbol represents the ending of the string here. Okay, first the A is replaced by X, and it checks for the consecutive B, and it checks for the consecutive C. Okay, in the same manner again it checks for the consecutive B and consecutive J. So then when I reach the blank symbol, then the machine is set to be accepted, right? Okay. Turing machine is also worked as a calculator. It is used for calculating some values like arithmetic computations, addition, subtraction, multiplication also. Okay, it is a superior machine for all finite automata, push-down automata, and linear bound automata. Okay. Here, it is the Chomsky hierarchy of languages. It contains regular language, context-free language, context-sensitive language, recursively enumerable language. Okay, recursively enumerable language. Here we will see the conversion of PDA and the conversion of CFG with an examples. Okay. Here for the production S tends to a delta of Q1 comma small a comma capital S is equal to, there is no string here, right? So it is epsilon. The same manner delta of Q1 comma small a comma S is equal to AB. For example, if it is S tends to small a capital B, it is represented by delta of Q1 comma small a comma S is equal to Q comma AB. Q comma AB. Okay, it is Q comma AB. Okay, in the same manner, B comma BB, B tends to BB. It is delta of Q1 comma B. That is equal to Q1 comma capital B. Q1 comma. It is the procedure for conversion of CFG to PDA. Okay. Here there is one more important topic in the push-down automata is pumping claim of context-free languages. As In finite automata, we'll take the S as the pumping lemma of regular languages. We'll take the S as S is equal to XYZ. If X Y power I Z belongs to L, then it is said to be regular language. Otherwise, it is not said to be regular language. In the same manner here, it is U V power I X W X power I Y is belongs to L. Then it is said to be context free language. Okay, for example, I will take the language L is equal to 0 power p, where p is a very important question. It is where p is a where p is a prime number. So L is equal to 0 power 1, 0 square, 0 cube, 0 power 5, 0 power 7, 0 power 11, and so on. If I take the string L is equal to 0 power 3, sorry, 0 power 5, 0 power 5, then it is represented by 0, 0, 0, 0, 0, U, UVW, XY is UV, XYZ. UV, XYZ. So here U is V, XYZ, and the V belongs to 0 and Y is belongs to 0. Y is belongs to 0. Then the pumping lemma rules U V power I X Y power I Z, where I belongs to 2. So it is U V square X Y square Z. That's equal to 0 here, 0 0 0 again 0 0 0. So it is belongs to 7. So uh, it is belongs to 0. Again we will check for one more input for cube. For cube I will check. So it is 0 triple 0 again 0 triple 0. So it is 9. It is 9. So it is not belongs to L. So the given grammar is not context free language based on the pumping limit pumping lemma of equal to power I b plus c power I. For example, is equal to I will take a square, b square, c square. Then by using pumping lemma, if I is equal to a b b c c, it is divided by double u v w x y. If I is equal to 2, it is a b b c c c. So it is not belongs to language. So the given grammar is not context free. Okay. The pumping lemma theorem is used to show the given grammar is not regular. That's it. Here construct PDA for the equivalent CFG. Delta of Q comma 0 comma S is equal to sorry. Okay, coming to the review of a push down automata and tuning mission. Here PDA means push down automata and NDPDA means non-deterministic push down automata. So deterministic is nothing but for one input there exists only one transition. That's all. What is the data structure in the push down automata? Stack is the data structure is in the push down automata. Okay. Two types of normal forms: Chomsky normal form and Greibach normal form. So the pumping lemma of context-free languages is here. The same manner, pumping lemma of regular languages S is equal to X, Y, Z or any three characters. The pumping lemma can be used to show that certain languages are not context-free. In the pumping lemma can be used to show that certain languages are not regular also. Okay. Coming to the definition of decision problem, it is used to find out whether a finite automata is accept zero or finite number and infinite number of strings. It is used to decide whether the machine will accept which type of inputs. Okay. Coming to simplification of context-free grammar, we have three procedures: elimination of useless symbols, elimination of null productions, elimination of unit productions also. Okay. So coming to the closure properties of context-free language, the context-free language is closed under union, concatenation, and clean closure. Content language is not closed under intersection and complement. Closed means if two languages L1 and L2 are context-free languages, then the union of two languages is also context-free languages. In the same manner, if L1 and L2 are two context-free languages, then the concatenation of two languages L1 L2 is also context-free language. A clean star or a clean closure is nothing but it is all possibilities of language. For example, if L is equal to A power n, B power n, then L star is nothing but A power n, B power n whole star is also context-free language. And coming to not closed under the CFLs are not closed under intersection and complement. Intersection is nothing but the common strings between two languages. If L1 and L2 are two context-free languages, then L1 intersection L2 is not necessarily context-free language. Maybe or may not be, and there is no fixed condition for intersection also. In the same manner, if L1 is a context-free language, then L1 may not be context-free language. L1 dash may not be context-free language. Okay, this is also the closure properties of context-free languages. Okay. Okay. Actually, the entire syllabus of in the entire syllabus of theory of computer science, you have major questions from finite automata and regular languages and context-free grammar and push-down automata, and we have very less number of questions from Turing machine and push-down automata. As these two topics, finite automata and push-down automata, is very important. The maximum questions comes from the same unit only. Okay. Okay, it is introduction about theory of computer science for your GATE subject, and maximum there is a problematic question from flat only. Theory questions from the theory of computer science is very less as compared with problematic questions. They give uh, finite automata and the languages. You need to find the machines along with the drawbacks of finite automata based on the pumping lemma theorem. Also, they asked about pigeonhole principle. And next, coming to CFG, CFG derivations, sparse trees, ambiguous grammar, how to eliminate ambiguity, and next one, conversion of CFG to PDA, PDA to CFG, and normal forms of normal forms in context free grammars. It is Chomsky normal form and Greek normal form, and you need to convert from CFG to CNF to GNF and GNF to CNF. Um, next, applications of context free grammar, applications of finite automata. Next one, minimizations of finite automata, minimization of finite automata. Okay, these are very important topics in the given GATE syllabus. Okay, and finally, you have very much practice questions in Geeks for Geeks website. You have all previous questions on GATE. Okay, I will show here. Here it contains the topics and along with the uh, objective questions also in for theory of computer science itself. Okay, and one more website is Solutions Adda. It contains the objective questions from the previous GATE and uh, from GATE questions. Here you have a plenty of questions along with your explanation. Okay, along with your explanation. So here we have questions like objective questions. You need to solve and you need to better to practice all the questions here. Okay, these two are very important websites for your GATE examinations. Okay, please concentrate on context free grammars and finite automata, push-down automata, and finite automata. Okay. Here, the important topics that you need to go through once again is here. Here you have the basic questions from this. From the introduction, you have basic questions. Basic questions like definitions and small problems. And here you have the conversion of RE to FA, minimization of finite automata, the limitations of finite automata, and NFA to regular expressions. Okay, finite automata with output, that is Mealy mission and Moore mission. Mealy and Moore mission. Okay, there is a rules for conversion from finite automata RE regular expressions. Okay, conversion of NFA to DFA. Okay, these are the questions from this. And coming to next one, it is very one important topic in this regular sets properties of regular closure properties of regular languages. And pumping lemma. Pumping lemma is used to show some certain languages are not context free and not regular languages. And about Myhill theorem, it is used to minimize. It is used to minimize the finite automata. It is used to minimize the finite automata by reducing the number of states and without changing the nature of the machine. Okay. Here, coming to second unit, coming to context-free grammar, there is a question like right linear to left linear grammar and derivation trees and parse trees, ambiguity, and how to eliminate ambiguity. And one more important topic is simplification of context-free grammar. It is reducing the number of productions in the given grammar without useless symbols and unit productions and epsilon productions also. And coming to normal forms, we have two normal forms, CNF and GNF. And the question may ask like convert the given grammar into CNF, convert the given grammar into GNF itself. Okay. And coming to pushdown automata, maximum there is only three problems: construction of PDA and PDA to CFG, CFG to PDA, and two stack PDA. These are the four main problems in the pushdown automata. And one more important topic is there is also closure properties and pumping lemma in pushdown automata itself. Okay, closure properties and pushdown automata. Uh, Closure properties and pumping lemma of these context-free languages. Okay, these are comes from second unit. Coming to Turing mission, they'll ask the types of Turing missions and the closure properties of Turing mission is very important in this undecidability, halting problems, and PCP problem and MPCP problem, modified post correspondence problem. Okay. These are Chomsky hierarchy. They may ask about linear bound automata and the limitations of linear bound automata. Why there is a need of Turing mission as we have linear bound automata. And coming to this extended Chomsky hierarchy. Okay, this is all about your theory of computer science introduction, and you may practice plenty of questions to get a very good score in this subject. Okay. Okay. And once again, I will tell that the two websites, Geeks for Geeks and Solutions Adda, are very useful for you people to practice a plenty of questions from all the subjects of GATE, which contains along with the explanations of the questions from GATE. Okay.